So we make use of the time evolution operator, UI, to define the transition amplitude in the most general way, and that is valid to all orders in V. This is the summary of our previous result. In the interaction picture, state at time t is a state at time t equals 0 multiplied by a time evolution operator in the interaction picture. And interaction picture is defined to be the Schrödinger picture wave function multiplied by the killing factor at this exponential factor kills the evolution of the state for the unperturbed state. And the time evolution operator UI running from t0 to final time t is the time ordered product of, usually we call the time ordered exponential of minus I over h bar integrated over time with respect to the potential in the interaction picture. The potential in the interaction picture, any operator in the interaction picture, is the Schrödinger picture's potential sandwiched by the time evolution operator of the unperturbed state. And actually it's this inverse time evolution operator. It is time evolution operator, this is the inverse. As we have already stated, we express our result in terms of the states of the unperturbed state. And our interaction is V in the Schrödinger picture, and that is acting for a very short time, short period, and in a restricted area. And before such a transition, the initial state is free, not free. The initial state has eigenstate of H0, which may contain potential, and final state is the eigenstate of the same Hamiltonian, H0. So what does it mean by F psi I t? So in the interaction picture, we have a time evolution, and here I and F are states of those Hamiltonian, and we ignore the time evolution of those states. So just like a time independent problem. So here I, F, we assume that N, state N, is the energy eigenstate of H0 with the quantum number N. That's it. And F t equals 0. The time evolution is not included in there. Okay. So initial state is in the Schrödinger picture. At time t equals 0, we prepare a state to be initial I. And I'm interested in knowing the transition probability. And in order to get the transition probability, we have to compute the transition amplitude from I to F. And we just try to compute. Right now, we don't know what it is, but in the interaction picture, we evolve the state to time t and just make a projection to the state F. And we will find that it seems to be the same as transition amplitude we have computed by making use of Schrödinger picture previously. In the interaction picture, state at time t is state at time 0, t equals 0, and multiplied by the time evolution operator in the interaction picture. Alright? And if I substitute t equals 0 here, at the time, Schrödinger picture can be interpreted to be the interaction picture, but at time t, everything is 0. So at t equals 0, interaction picture state is the same as Schrödinger picture state, and we declare that we have initial state, pure initial state with I, index I. So if I want to compute the state in the interaction picture at time t, I just multiply initial value in that picture that is just exactly the same as I, and multiply the transition time evolution operator in the interaction picture from t equals 0 to t. Alright. So this was our question. Let us simply compute this. I substitute this previous result in the side ti here, and we know the all order result expression for the time evolution operator. That is a time ordered exponential of the potential in the interaction picture. Let us expand this in powers of v, and the leading term is just 1, and this is fi, that means delta fi. Right? The next one is just a single integral of the potential, and h0 is applied to the final state and initial state to have this factor, and the matrix element from initial state to final state for the potential in the Schrödinger picture. By the way, this is exactly the same as the transition amplitude we have calculated by making use of Schrödinger picture. But at the time, we stopped the calculation at order v, and we did not include the contribution of order v squared. Okay? So it seems to be, we can guess that there is some relationship between this matrix element, right hand side in the interaction picture, and left hand side is just time independent state and final state. It seems to be the same as transition amplitude. However, we do not have full expression that is valid to all orders in V. So let us check if our guess is really true to all orders in V or not. When we computed the transition amplitude by making use of Schrödinger picture, we have written the state at time t as an expansion in terms of the state, eigenstate of H0. And we factor the time evolution due to that H0 only. We pulled out that factor and we treat the remaining factor to be the ck of t. Right? If I multiply the inverse of the time evolution operator, okay, if we express this one by H0, H0 is replaced by energy of the kth state. So this can be a single operator, even though in this expansion Ek varies depending on the state k. If I replace H0 with H0, then I can factor this operator out because the CKT is just a number. So if I multiply this inverse time evolution operator for the state, for the unperturbed Hamiltonian H0, then I would get this kind of expression. And right-hand side is just linear combination of the unperturbed state. By the way, the left-hand side is what it is. But left-hand side, if I make use of this definition of interaction picture wave function, this is just the interaction picture wave function at time t. And let us recall the transition amplitude. Transition amplitude is, for example, if I prepare initial state to be I, and transition amplitude is over factor in the expansion of the amplitude, final state amplitude. Okay? So coefficient of some final state f. That means find out the coefficient of f in this expansion. Okay? So actually, if I want to compute the AFI, this is the transition amplitude, that is CF at t goes to infinity. And with the condition that CK0 is delta Ki, that means at t equals 0, only I states survive and all the other states are vanishing. Alright, so if I want to compute the CF, what I have to do is just multiply F bra, right? F state. So if I multiply bra vector of F state, final state, then what I get is just the CF. So by definition, F multiplied to the state in the interaction picture at time t goes to infinity is actually the transition amplitude. So this is just approximate one that is valid up to order V, but this is true to all orders in V. So we can make use of this fact that transition amplitude is just simply calculable by evaluating the wave function at t goes to infinity in the interaction picture and then project out the state f. That is one of the eigenstate of unperturbed Hamiltonian H0. Alright? So, in summary, we can define a matrix which is called the S matrix. S matrix is just a matrix that is a time evolution operator. Time evolution operator. This was connecting the initial time was t0 and final was t, but just to release them to minus infinity to here. This is plus and this is minus. From minus infinity to infinity. Okay? Then this is the same as this, except that I put the lower bound of time to be the minus infinity, upper bound of time is plus infinity. Then, if I want to compute the transition amplitude from initial state to final state, what we have done in here is just a selective one. Just give me I and F and we calculate it one by one. But that can be done by projecting out the state, initial state I and final state I, F, to this matrix. So this S matrix is valid to all orders in V, and we can compute the transition amplitude from the initial state to final state by making use of this. That's it.